All right, hey everybody, it's Mr. Stone here again. Again, here we are in the virtual classroom, the virtual school, Upper Canada Virtual School classroom, learning about physics. So this is grade 11 University Physics, Unit 1, Lesson 2. And we're going to talk about displacement and velocity. So hopefully you guys are getting a hang of Teams and the Weebly site and figuring out all the places that everything exists and how to get stuff to me and how to contact me and all that sort of stuff. It is a learning curve. I know I myself am learning all kinds of things, and we're going to figure this out and we're going to have a great time. All right, so let's keep talking about physics. Okay, so we're going to talk about displacement, velocity. Remember, these are vectors. So that's the first thing I want you guys to remember is what is a vector? Remember, vectors are things that have a size and a direction. So we know how far something is going in a certain direction, how fast it's moving in a certain direction, something like that. Okay, so displacement was one of the examples we gave, and that was a change in position. We can say D is a position here. That should be a vector. I apologize. That should have a hat on top. Okay, so change in position, D, of an object with respect to a reference point in a given direction. Now that last thing, that reference point, that's very important. Where we decide our reference point is can change what we mean by what its displacement is. For us to define a displacement, we have to define an origin, right? We have to define where, like put a Cartesian coordinate system, like an XY plane or just even a line somewhere and put a 0 somewhere on it. That could be at the point that we're talking about. That could make things easier. It could be somewhere else. But we have to define that reference point for us to actually define how far away we are from something. We can't talk about 15 meters west when we don't know where we're starting from, right? So that reference point is actually quite important. And a frame of reference, one of the things we're going to talk about today is vitally important in physics. And defining that frame of reference can really make a question easy or difficult. Okay, so we got to keep that in mind. Velocity is another thing that was a vector. It's a rate of change of position with respect to time, but it's the rate of change of position. So position is a vector itself. So the rate of change of that is itself going to be a vector. So here we can say, that the velocity, v, with the hat on top, remember that hat denotes a vector, is 2.5 meters a second forward. So that has to be a vector because it has an arrow, and a square bracket direction. Average velocity, we already discussed last one. We discussed average speed. So now we can talk about average velocity being the total displacement, delta d, divided by the total time elapsed, delta t. Right? So this is our another equation here, the vector form of the speed equation. Right? Just like we had the average speed equation, this is now as a vector, okay, in a certain direction. And there's some subtle differences here. Like let's say we're running around a track. A track is 400 meters to go from the starting point all the way around, like so a running track, right? When we talk about velocity, right? Sorry, speed. For us to calculate the speed of a runner going around those 400 meters, all we would need to do is time them, right? And we take 400 meters, divide by their seconds that they took them to do it, and we would get a speed, right? And we would have a speed in meters per second. What would be their velocity for that same run? Now remember that displacement is the change in position. And when you run around a track, let's see, draw up here, can you guys see this? Here's a track, right? And there's going to be some point here that's our start and finish. So we're going to go around. And when we finish our run, we're in the exact same position as when we started. So our displacement for that run, our distance was 400 meters, but the displacement will be 0 meters. Okay, our displacement will be 0 meters because we didn't actually end up going anywhere in terms of displacement. We did not displace ourselves. Our distance is 400 meters, but our displacement is 0 because we ended up in the exact same position. And so the concept of displacement is pretty subtle, okay? And so really, this runner, their average velocity is 0 meters a second. I'm sorry, but you ran 0 meters a second as a velocity. Oh, also notice I didn't put a direction on that because 0 doesn't really have a direction. It's not forward, it's not backwards, east or south or west. It's 0. It's our null. It's our nothing. Okay? All right. So now I've added this video. I'm going to add this to the links. It's a quite amusing video.
We're used to seeing things
a bit
from
old,
a particular point of view.
but what I'd like
that
you to
is,
do
from a
is
particular frame of reference. And things look different to us under.
what I'd like you to do is to go and watch this. This will be in the description of the video. It'll be on our Weebly. I'd like you to watch this video. It's very old. It's about, I think it's 60 years old now. One of these are, it's actually University of Toronto professors from 1960. One of them only just passed away recently. It's a brilliant video. I'd like you to watch the whole thing. It's about half an hour long. I know it's pretty long. Actually, maybe don't even watch the whole thing. Watch the first like 15 minutes of it to give you a sense of frames of reference and how important they are. I don't want to waste our video watching this, but feel free to go on the on YouTube and watch this video. Okay, it's brilliant, and it gives you a sense of why these frames of reference are crucial and are important for us to quantitatively understand things in physics. Okay. So let's talk about now in terms of one direction, okay? In one dimension, sorry. Once we've defined a frame of reference, vector addition is very simple, okay? If you define a frame of reference, if you put like a meter stick down with a 0 point on it, vector addition is just adding just like regular numbers. We can treat these things just like numbers and we can add them. It is a little bit more complicated. We have to be a little bit careful in, are we adding or subtracting? But, or is it a positive or a negative number? But really adding vectors is just on one dimension, left, right, up, down, something like that, north, south, east, west, is pretty straightforward. So let's try an example here. So we have a dog. It's initially 4.3 meters away from you. So there we've defined a reference point. And that dog, let's say the reference point is me. That's our 0. The dog is in front of me 4.3 meters. That's our first position. They run away from you 12 meters to fetch a stick. How far away is the dog after it gets the stick? Now that's pretty straightforward. You can answer that yourself, right? We can say 16.3 meters. We know the answer right away. I'm doing this as an example of how we can do this with vectors, and I wanted to start with a very simple problem to help us to visualize this, because we can see that, right? It's 4.3 meters away from us, and then it's farther away, so we're just going to add the numbers. So the dog starts off 4.3 meters away from us. This arrow that I've put on the ground here represents our frame of reference. So there's our 0 point, right? We've defined our 0 point to be the person throwing the stick, and the dog who starts off at a position D1, that's our first position. That's our first vector, right? We could draw an arrow to represent that first vector. And then eventually he's going to end up at D2, which is going to be a new vector, much larger, and the displacement between them, the change in the position from 1 to 2, is going to be our displacement, delta D. And that's going to be equal to 12 meters, right? Okay. Oh, and so that's 12 meters. Forgot I had something under there, right? And we know that that's going to be D1 plus D2. Okay, no, sorry, that should be minus. Apologies. So yeah, I'm learning too. Okay, so the difference between the two is going to be our displacement. That's how far the dog has run, and that's 12 meters. So let's do this now from a mathematical, like in the way we do these physics problems. Write down what we know, what we want to know, write an equation, and solve it, and go from there. So what do we know? We know that the initial position of the dog is 4.3 meters forward. That's what that expression tells us. D1 as a vector. It's 4.3 meters forward. The displacement, the delta d, the change in position, is 12 meters forward, right? Because he got farther away from us. He's leaving us. He's going 12 more meters away. And we want to know what his new position is going to be, d2. All right, we can have our formula that d2 minus d1 is the displacement. And for us to get d2 by itself, we just have to take negative d1. We can add d1 to both sides, or in doing a little cheat mathematically, we can bring the negative d1 over. It becomes positive d1, and so then we can end up with an expression for d2. It's going to be the displacement plus the original position. Right? This is our displacement, 12. Here, write it down. It's going to be our 12, our displacement, and we're going to add to that our initial position, and we're going to get 16.3, which is what we expected, right? And of course, we're going to have to round because there's no decimal places on the 12, one decimal place on the 3, so we have to round it to the lowest number of decimal places, in this case 0, so we have to round that to 16 meters, and of course, therefore statement. All right, so again, anytime we do math problems in physics, always the same idea. Givens, unknowns, a formula, solve, substitute, answer. Okay, and statement at the very end. All right, so pretty straightforward problem, but writing it down, things can get a bit complicated and can get a bit confusing. Okay, so we want to write it all down, but it all does make sense once we think about it. What if the dog runs the other way? What if the dog's running towards you now? It starts off coming towards you at 4.3 meters. So this distance here, this is the initial position vector. D1 is that way. But now the dog is going to end up at a position behind you because they ran past you. Okay? And again, the same mistake. Apologies. Oh, that should be a negative there. D2 minus D1. Okay, so we're going to take D2 minus D1 to get our position now. All right, and again, this is our 0 point, and we want to know this vector. And notice now this vector is pointing in the negative direction. In our frame of reference, right, we put positive numbers going to the right, forward. Right, we also said this is the forward direction. This is the backwards direction. Apologize, it's hard to write on this, but we're going to end up with a negative answer. So let's make sure we have a negative answer as our final answer here. Notice the vector, the displacement vector is going past us, so the displacement vector is also going to have to be negative because it's going in the negative direction. All right, so let's think about that again. We started with a positive position vector. Our displacement vector is going to be negative because it ran past us 12 meters. So we're going to end up with a negative final position. So let's see how this works mathematically. So D1, same idea, but D2 now is going to be 12 meters backwards. Notice I wrote this as positive 12 in the backwards direction. Right? So this is a positive number using the backwards frame of reference, which isn't the same as the frame of reference from D1. So we're going to have to change that. We're going to have to change that into negative 12 meters forwards. So we're using that in the same frame of reference, right? We can say that the displacement was negative 12 in the forwards direction. We're going negative forwards, which is the same as backwards. Okay? And now it becomes quite straightforward because we're still looking for D2, same idea, but this time when we substitute in our displacement, it's negative. So we end up with a negative answer of negative 7.7 meters forward, or if you want to make things easier, if you don't like that negative 7.7 forwards, just say positive 7.7 backwards. Right? The dog is almost 8 meters behind us. Right, apparently I threw the stick behind me and it ran past me. And I got a final answer of the dog ends up 7.7 meters behind you. All right. So it can be a little bit subtle in terms of how these questions can be solved. But in one dimension, it's pretty straightforward. Once we end up everything all in the same frame of reference, we just add them just like numbers. So here, this is a vector. These are two vectors that we're adding to each other. But since they're both in the same frame of reference, I can just treat them like they're numbers. Okay, they're just numbers on a number line. We can't add these two numbers here. We're going to get 16.3 again, which is wrong. Right? We cannot add or subtract these numbers because they're in different frames of reference. We have to be in a consistent frame of reference. This does bring up an interesting point that we have to be consistent, but there is no correct frame of reference. One of the big fundamental ideas of Newtonian physics, Newtonian named after Sir Isaac Newton, is that there is no correct absolute frame of reference. The laws of physics are the same in all frames of reference. It doesn't matter which one you pick. We're arbitrarily picking. I could have done the exact same problem all using the backwards frame of reference. In that case, my d1 would have been a negative number. And then to find my d2, I would have been taking 12, take away 4.3, and I would end up with 7.7, positive 7.7, backwards. I would have had the same answer. There is no correct frame of reference. There's just one that is usually more straightforward for the problem, which is easier to deal with. Okay? Awesome. So big idea there. There is no correct frame of reference. Newtonian laws of physics exist correctly in all frames of reference. A little caveat that it's all inertial frames of reference, non-accelerating frames of reference, but that's different. Okay, so as long as your frame of reference is stationary, or as long as your frame of reference is not accelerating, then that's true. If it's accelerating frame of reference, things get a bit weird. Okay, but that's well beyond what we're talking about here. All right, now what about the velocities? If it takes 0.4 seconds for the dog to get to the stick, what are the velocities in each case? So running away, we knew that our displacement was 12 meters forwards. It was going 12 meters farther away in the forwards direction, so we end up with 30 meters per second forwards. That directionality that was in the displacement vector carries on in the velocity vector. Whatever whatever direction you have in your math, whatever you're doing, whatever calculation you're making, whatever you're doing something like this, there is no directionality to the time. So when we divide them, we end up just carrying on that direction from our problem. In the same way that running past, we end up with 12 meters going backwards, right? The dog is going 12 meters in the backwards direction. We end up with the same numerical quantity, 30 meters per second, but now we changed the direction of our vector, of our velocity. It's now going to be 30 meters per second backwards. Okay? Which makes total sense, right? We said that in the beginning of the problem. The dog is running away from you, or it's running past you, right? And that shows up in our... So really what I'm taking a very simple problem and showing where the mathematics leads into these bigger ideas of vectors. And we'll see where this really is important is when we're trying to add vectors in 2 dimensions. If we're trying to add vectors that are not collinear, collinear just means in the same direction. If we're adding two vectors that are not on a line, like say backwards, forwards, somewhere along a one-dimensional line. Let's say they're in a plane now, north, south, east, west, on some flat plane. We have to do a lot more work, and it's going to be a lot more complicated. Okay, so we're going to break it down into steps. So first step typically is just draw a picture. And this is true in a lot of physics problems. It doesn't matter what you're doing. Drawing a picture actually makes a lot of sense in terms of helping us figure out what we're trying to do, what the goal of our problem is, and the easiest way to get to that goal. Okay, so once we have our picture, we can define a coordinate system. That's the same thing as saying define a frame of reference. We need to define what's positive, what's negative, what's going to be our frame of reference, what's going to be our Cartesian coordinate system, our XY plane we're going to slap onto the system to help us figure it out. And again, that's arbitrary, but usually we can do it in a way that can make things a little bit easier for ourselves. Okay? So once we now have our picture and our coordinate system, we're going to take our vectors and we're going to break them up into pieces that are in the direction of those coordinate systems. We're going to call those components. So let's say I define a frame of reference that's north, south, east, west. Okay, and my vectors aren't in those cardinal planes; aren't in those directions. I'm gonna have to take those vectors. This is the beautiful thing about vectors: is I can take my vector, and I can make it into two vectors, which are added together to make my original vector. Sorry, I'm just trying to get my pen here. So I can take my vector, let's say. So I have a north, south, east, west coordinate system, let's say. Call this north on top. Okay, this vector is not in one of those directions, and that vector, what this is showing me here is this is sort of like my start point, and this is sort of like my finish point. That's what my vector says. If I'm thinking of this as a displacement vector, let's say, I started out here at D1, and I'm going to end up here at D2. Now, it doesn't matter. I can get from my start to finish point by also going in the easterly direction first. Let's call this D1, and then heading up in the northerly direction, D2. Okay, I can do the same thing as my displacement vector here by first going east and then going north. Or also, if you want, you can go north and then east. It doesn't matter. That's the same. That's D2 there, and that's D1. It just makes a rectangle. Those have the same lengths, and we're all good. So whatever my frame of reference is, I can break it up into pieces, two new vectors, in those directions that I'm using. Okay, it doesn't matter what the vector is. I can always break it up into pieces. And those two pieces are dependent on my frame of reference. I could have defined a frame of reference that is, in the direction of that vector, and then I could only have, one component in that direction. But typically I'm going to use north, south, east, west to help us break these down and then add them. Because once I've broken them down, I've got a whole bunch of vectors all in the same direction. Let's say I have a bunch of east-west vectors and a bunch of north-south vectors. Then I can add those ones that are all in the same direction because they just behave like numbers, just like a one-dimensional system like we talked about in the previous example. And then once I have all of the x, let's call it, if I can make my life easier by calling this x and y, right? I can add all the ones that are in the x direction and add all the vectors that are components that are in the y direction. Add them all up. I now have two new vectors, total vectors, that then I can break up into A, B, C. I can use Pythagorean Theorem and use some trigonometry to find my angle, and I'm done. Okay, I know that sounds like a lot, and it might not be very clear when I do it like when I just write out the steps, but let's do some examples to make things easier. Okay, let's do an example. So let's say I have a football example here. Let's say I have a wide receiver. This wide receiver is first going to run 8.5 meters east. Right, so this is before the snap or something, right? Before the ball is snapped. They're going to run east. Then they're going to run north 32 degrees east. Now, what the heck does this mean? 13.2 meters north, 32 degrees east. What this convention, the convention here for directions, is pretty straightforward actually. The first letter represents it's mostly going north. So this would be like, so here, that's my example here, using north, south, east, west. This is mostly going north, but then the correction is 32 degrees east. So it's mostly heading north, but then there is a correction of 32 degrees east. Okay, so it mostly heads north, but then these sort of go together. It's saying north 32 degrees east. Okay. Then the ball, that's when the ball is snapped. They ran that far, and then after they've gone that far, they've then ran 4.2 meters west, and they're tackled. Okay, so first determine the total distance and their speed. So this is the scalar question. And then we're going to have to do the same thing for displacement and velocity. So this is a scalar problem, and this is a vector problem. Okay, basically the same problem. One is with direction, one's without. So the scalar problem is pretty straightforward, right? The total displacement, we just take the total distance, take the three distances, add them up, and we get a final distance of about 26 meters. Speed is just going to be how far they went divided by the time, and that's about 4 meters a second is how much they ran. Okay, rounding to two significant digits, we end up with 4 meters a second, 4.0. So final answer, wide receiver's total distance is 25.9 meters, and their speed is 4 meters a second. Okay, I know I went through that very quickly, but this is pretty straightforward. This is just a simple speed problem. If it's a scalar, if it's asking for distance or speed, just add the numbers. Okay, just add the numbers and then use our formula. We have our final answer. Scalars, we've done this before. It's pretty straightforward. All right, now, if we're going to do part B, question B, sorry, which was do the same thing but as a vector, it's going to be a lot more complicated. But we can break it down into those 5 steps, and it can be pretty straightforward. We just have to do a little bit of work. So first off, we're going to draw a picture. So we first went east, then we went northeast, and then we went west. Notice this is not a scale diagram. I just did it, this is 8.5. 13 is bigger than 8.5, and 4 is about half the length of 8.5. So it's not exactly to scale, but it's pretty close to give us a sense. It's not meant, like if you did this to scale, you could just put your final answer in and use a ruler to find it. But we want to do it more accurately with these components. Okay, so we know that our starting point is here. Also, notice what I've done. I've drawn the vector from my starting point here. This is where I start. This is my first vector. It ends at this arrow. My next vector I draw from the arrow of the first one. It's from tip to tail. Okay? That's what your math teacher will say one day. We add vectors from tip to tail. We then, right, because we've gone that far. Now this is going to be our new starting point, and we're going to add our new vector, and then so on and so forth. And our final answer, right, this is our final finish point, right? So our final answer, we're going to draw an arrow from the starting point to our finish point here. Okay, so we draw our 3 arrows, tip to tail, and then our final answer, the final displacement here, sorry, I should put a delta there. The final displacement is going to be from the original starting point of D1 to the finish point of D3. All right, because that's where he's going to go. But my displacement vector, sorry, is going to be that big red arrow there. And we have to find out how long it is and also what this angle theta is here, because you can see it's mostly north, but then it seems to be about, looks like my poorly drawn picture, about 45 degrees or so. Okay, so just looking at our picture, we can guess, we can do a quick little guesstimate that it's gonna be longer than 13, right? This one's less angled, so this is longer, so it's gonna be about, 14, 15 meters, and the angle is about 45. So that's our guess. We can keep that in mind. All right, so there's our first point. We're done. Step 1. We've drawn our picture. We've labeled it. When you label it, put your directions on there, put arrows on your symbols, and we're good to go. All right. Now that we've got our picture, we can put our coordinate system on it. We can put our frame of reference on here. And I'm going to use north, south, east, west, since that's what the question gave us, quantities in north, south, east, west. So let's do that. So we can define our cardinal directions here as north, south, east, west. And once I've done this, I can now decide which of the directions, north or south, or east and west, are positive and which ones are negative. Looking at the horizontal directions, I can see that I'm mostly going in the easterly direction. So I want east to be positive. And I'm only going north, so I want north to be positive. This is completely arbitrary again, but this is I've chosen those directions because it's easier in my question. I don't have as many negatives to worry about. I don't have as many places to make mistakes. All right. So now that I've got those that coordinate system set up, I'm ready to break it up into the pieces in that coordinate system. Oh, and also I can just make my life simpler by calling these x and y. Just like we do in math class, the x direction is horizontal, the y direction is vertical. So let's break them up. These are my three vectors, sorry, d1, d2, and d3. d1, pretty straightforward. We know that it's going east. Its x direction component, east. And positive 8.5, because I know that the easterly direction I called positive. So when I break it into components, that directionality is still kind of there. It's still hidden, but it's hidden in the plus or the minus. So if you see a distance here, an x component of a distance, 8.5 meters, you can recognize that that is east. It's nice here. There is no y component. We are only traveling 8.5 meters east. We are not deviating from that in the y direction. Now d2, this is more complicated. We have to do a little bit of trigonometry, right? Because this is now going to be a vector not in one of those cardinal directions. So I have to break it up into a y direction and an x direction. All right. And now we know that this is right here from the question. This was 32 degrees. All right. I'm just going to switch here. That might be easier to see everything. We know that that was 32 degrees. We can then also say that this angle here is going to be 58 degrees. Wow, that got ugly. Let's try that again. That's going to be 58 degrees. And you'll see why I care about that. But for me to go from this starting point to this finishing point here, it's equivalent for me to first follow this red arrow in the x direction, and then follow the blue arrow in the y direction. I'll end up in the same spot. So I can say that me going in 13.2 meters north, 32 degrees east is the same as going 13.2 meters multiplied by the cosine of 58. Hopefully you guys remember some of your trigonometry here. If I want, this is 58, so this is my adjacent side. This is my hypotenuse. Adjacent over hypotenuse is the cosine. So cosine of 58 is going to be this side, this adjacent side, divided by that side. So solving it multiplies by both sides. Multiplies by 13.2. Okay. I went through that pretty quick, but just remember what that cosine of an angle is the adjacent divided by the hypotenuse. So then for us we know that the hypotenuse is 13.8, so I can multiply both sides by the hypotenuse to solve for the adjacent side. So the adjacent side, in this case d2x, is going to be equal to the hypotenuse, 13.2, multiplied by cos of 58. And plugging that into our calculators, we get 6.99 meters, which makes sense, right? This is 13, it's about half-ish, so it's about 7 meters in the easterly direction. I know it's east because my answer is positive. I know that positive, going back to my, whoa, that's a long way, the positive direction here is east. So when I write it down as a component, my final answer, not my final answer, but my component answer is 7 meters positive. So that's in the easterly direction. Doing the same thing for y, now I want d2y, which is this guy over here. that's going to be the opposite side. So it's opposite divided by hypotenuse. So we're going to be using the sine ratio. So we end up with 13.2 multiplied by sine of 58, and we end up with 11.2 meters. Notice in my picture, see, these are vectors, right? So I put a vector sign on them. However, when I write them as components, I don't need a vector sign. It's telling me the direction in the label, x here. And it's telling me that it's positive, so it's in the positive direction, which was north. Oh, that should be a y there. Uh-oh. Okay. So for me to go in the direction, in the displacement direction here of 13.2 meters, north 32 degrees east, the same as then I first go 7 east and then go 11 north, and I'll end up in the same spot. So I've broken it up into these two pieces. Right? Notice the color coordination here. X is the red color and Y is blue. Last one, D3, pretty straightforward again. We know that it's going west, so we have an X component and there is no Y component. But notice now, because it's west, I'm going to have to call that negative 4.2 meters. That negative there is telling us that we're going in the westerly direction of 4.2 meters. All right, so there, done step 3. I've broken it up into red components, right? There's my X components, and I have Y components as well. All right, and all I have to do now is put all those red numbers together and all the blue numbers together. So step 4, add all the components that are all in the same direction. So all the X pieces and all the Y pieces. So in the X direction, I have 8.5 meters from the first one, right? Because it said 8.5 meters east, so that's going to be positive 8.5. Multiplying by cosine of 58 gave us the 7 meters from D2, or 6.99 meters. And D3 was 4.2 meters west. So that's negative 4.2 meters. Add it all together, 10.9 meters in the X direction. Same thing for the Y's. I had no Y from 1 or 3, but looking up the, multiplying by sine for D2, I ended up with D2Y. The Y direction of D2 is 11.2. So I get a final, since I didn't get any extras from 1 or 3, it's only that Y component from 2. So now I have my final dx and dy. So this is telling me that for my final answer, I'm going to go 11 meters east because it's positive and 11 meters north because it's negative. And I'm going to get a final answer, which is this black line here, this black vector. And we just have to figure out what that is, right? And we can do that using Pythagorean Theorem. So now we're on our final step. Okay, I know we've done a lot here, but we have our last little bit to do. Step 5, we're going to use Pythagoras, and we're going to figure out what the length is. So we square the two, add them up, take the square root, and we get 15.7. That's pretty close. What did I guessed 14 or 15? That was a bit bigger, but okay, 15 meters, 16 meters-ish. And we want the angle. Now, easiest way here to get the angle, always divide the smaller number by the bigger number, okay? You always take in this case is 10.9, divide that by the bigger number, so 10.9 divided by 11.2, and then take the inverse tan. Because tan, remember the ratio for tan was, let's write this down, tan is opposite over adjacent. So if I take the smaller number divided by the bigger number, it's always going to give me a number less than 45 degrees, and we don't have to do extra work. Okay, so if you get a number greater than 45 degrees, you've got it upside down, just flip it, and we end up with 44 degrees as our final answer. I guessed 45, so pretty close. Now, how do we write this as a final answer? We know that the scalar portion, the magnitude portion of our final answer is 15.7. We got an angle here as 44 degrees, right? This is 44 degrees there. What's my final answer going to be? Now, which direction is it going most? The y direction is larger, right? So it's mostly going north, and then a little bit, there's a correction in the easterly direction. So we say it's going, using two significant digits. It's 16 meters north. It's going mostly north, and then we're correcting it by going 44 degrees east. All right, so it's mostly north because the dy was larger than the dx, and we ended up with north 44 degrees east as our final answer. And of course, oh gosh, put a therefore statement, put a box around it, and we're finished. And put a period, Mr. Tom. All right. So that was a lot. That's a big problem. Let's go back here. That's a pretty big problem, and we can see all the steps that are involved, and it takes a while, but once we break it down into the pieces, it all makes sense. Right? We can't add vectors. We can only add components in the same direction. Right? We can't just add numbers, right? We put with the numbers. It was 4.2 and 8 and 13, and we ended up with a number of 16. So we can't get that number unless we add all the pieces that are in the same direction, and then make this new triangle that we can then use our trigonometry to find the answer with. Okay. So then it did ask us to find the velocity, which is just going to be, oh, that's not correct. That should be 16. Sorry. What is it? 16. So 15.7. This should have been 15.7. I copy and pasted wrong from the other problem there. So this is using now vectors. The velocity is going to be the displacement divided by the time. I should put meters on there, not cats per donut. 15.7 meters divided by 6.4 seconds, and we get a final answer of 4 meters per second. And remember, the directionality carries on to get our final answer. So the wide receiver's velocity now, velocity, not speed, is going to be 4 meters per second north, 44 degrees east. Oh, and really I should get rid of that 4 there. That's not right either, is it? Let me just check that number. That's not a correct number. All right, I fixed it. I apologize. Sorry about that. Copy and paste is wonderful, but you can miss something sometimes. Anyways, okay, so the oh, I didn't change it either yet. Okay, I forgot. My goodness, Mr. Stone. All right, let's try that again. Wow. Okay, so I'm a bit rusty. So that's 15.7 meters is our displacement divided by the time, 6.4. We end up with a final answer of 2.4 meters per second north, 44 degrees east, which is less than the speed, right? Because we're only looking at the starting point and ending point, not the path to get there, right? The path was much longer, so the speed would have been much larger, right? So final answer. Oh, am I here? Okay. You can put that down. Rounding it to the nearest, to the 2 significant digits, we get 2.5 meters per second north, 44 degrees east. All right, and there's my final answer after doing all that work. So now it's your turn, okay? So we're going to practice here with our trigonometry. We're going to break up vectors into components. And then once we have them into components, we can add them all up and we can get a final displacement. All right, so that's what this is. These problems here are just calculating displacements. Okay? All right, so I've been talking for about 45 minutes. It's a pretty long lecture. Sorry about that, guys. I talk a lot. All right, so I hope you guys are doing well. Again, when you're watching this video, go to the details, go click on that link to that frames of reference video. That's another piece of your homework. Make sure you watch that. It's really cool. You can add some comments if you want, or send me some commentary about it, or ask questions if you want. Frames of reference are critical to physics, defining where the frame of reference is. Okay, and picking a frame of reference that's convenient and useful for us. All right. Okay, so work on those problems. Um, again, this worksheet is on the Weebly. That'll also be in the links in the description. Solutions are also in there too. Okay, all scanned and ready to go. So best of luck and stay safe, and I'll be talking to you later.